To finish this section, we're gonna do one more deep dive into yet another fundamental aspect of how JavaScript works behind the scenes, and that's memory management. In this first of two parts of memory management, we're gonna learn all about primitives, objects, and more importantly, object references. Now, first of all, what does memory management actually mean? Well, memory management in the context of JavaScript is how the JavaScript engine allocates space in memory for creating variables and later frees up that memory space which was taken up by variables that are no longer needed, so that our applications run smoothly and efficiently without running out of memory. So basically, this lecture tries to answer the question, how and where are variables created in JavaScript? Now, unlike lower-level programming languages like C or C++, where developers actually have to manually reserve pieces of memory for their variables, JavaScript automatically manages the memory behind the scenes for us. This makes writing code a lot easier and faster, and it reduces the risk of introducing bugs like memory leaks. So this sounds great, but how does it all work? Well, to give you a broad overview, every single value that we create in our applications goes through something that we call a memory lifecycle. So in this lifecycle, first a piece of memory is allocated whenever we create a new value, for example, to assign that value to a new variable in our code. So essentially, each time we declare a variable with a new value, no matter if it's a single value or a huge object, the JavaScript engine will automatically reserve a piece of memory to store that value. So the value that is being held by the variable that we just created. In this example, it's to store 23.7. But again, it could be an object or a function or whatever we want. Then, as the app runs in the user's browser, the allocated piece of memory is used whenever the stored value is being accessed, for example, to write, read, or update the value. So this part is pretty obvious, but it's important to mention that this is also part of the memory lifecycle. And finally, what happens when the value is no longer needed? Well, in that case, at the end of a value's lifecycle, the memory it occupies gets released. Or in other words, when a value is not necessary anymore, it's deleted from memory, and the freed up memory can then be used for new future values. And we're gonna learn later how exactly that happens behind the scenes. But for now, in this lecture, let's start to look at the first step in more detail, which is memory allocation. Now, the main thing to understand about memory allocation in JavaScript is the fact that for different types of values, memory is actually allocated in different places in the JavaScript engine. But what are those different types of values? Well, remember from earlier in the course that in JavaScript, values are either a primitive value or an object. So primitive data types are numbers, strings, booleans, undefined, null, symbols, and big ints. Then everything else is objects. So that includes objects created with the object literal, arrays, and even functions. So all those are, in fact, objects. So those are the two types of values that exist in JavaScript. Next, we need to remember about the JavaScript engine itself. So the engine has two main components: the call stack, where functions are executed, and the heap, where objects are stored in memory. And from this, we can already start to understand how memory is allocated for different data types. So again, as I just mentioned, all our objects will get stored right in the memory heap. Or in other words, it's the memory heap where memory is allocated for objects. On the other hand, all primitive values are going to be stored in the call stack, where our functions run. And in detail, primitive values are actually stored in the execution contexts in which they are created. Now, there might be some exceptions to those rules because modern JavaScript engines are highly sophisticated and dynamic, so that, for example, they might store an extremely long string, which is actually a primitive, in the heap, so that the call stack where strings are usually placed can be optimized. But in general, as a mental model, this is how memory allocation works, and it's really all you need to know. So, in summary, memory for objects is allocated in the heap and for primitives in the call stack. But that's actually not all. So, besides primitives and objects, there are also something that we call references to objects, and these are also stored in the call stack. Now, what do I mean by object references? Well, let's find out, because references to objects are one of the most important things that you need to understand from this video, and I would actually say the most important thing. So, here we have a piece of code that we'll go through together and analyze exactly what's gonna happen in both the call stack and the heap as the code runs. So, when the code starts executing in the first line, the global execution context is placed on the call stack and the value of the variable name is set to Jonas right in the variable environment of this execution context. That's because Jonas is just a string, which is a primitive, and so, therefore, this value is stored right here in the call stack. Now, technically, these primitive values are stored in the variable environments of execution contexts, but since these actually live in the call stack, we just say that primitive values are stored in the stack. Next up, the age is calculated by calling calc_age, which is going to create and place a new execution context on the top of the stack as always. And so now, the values created in this function will be stored in their corresponding execution context. So again, in the call stack, because the variables now and x both contain numbers, and therefore primitive values. And primitive values belong in the stack, as we already know. Then the function returns, and its execution context pops off the stack, and with it, the values that it was holding in its variable environment are also gone. The returned value of 46 is stored as the age variable in the global execution context as well. Next, we declare yet another variable, this one called newAge, which is simply set to the same value as age. So the value of 46 will also get stored in the stack as newAge here. Then in the next line, we increase the value of newAge by 1, making it 47. Now, as we update newAge from 46 to 47, the primitive value stored in age stays, of course, at 46. So again, age, which is where the original value came from, remains unchanged. So each of the variables holds its own copy of the value at all times. Now this is pretty intuitive, but it's very different from how objects work, as we'll see in a minute. And so, speaking of objects, we create an object right here in the next line called location. And where are objects stored in the engine? That's right, this object will live in the heap. So that's where the engine stores objects. But now, if we think about this, how will our code actually know that this object is supposed to be called location? Or, in other words, how will we be able to use this object in the rest of our code? Well, that's where the concept of reference comes into play. So the way this works is that in the execution context, the variable location will actually hold a reference to the object. So again, location will not be the object itself, but just a reference to the object in the heap. In technical terms, it's the memory address of the object that will be stored as the value of location. But that's not really that important. What you need to understand is that variables in the call stack do not hold objects themselves, but references pointing to these objects. Now, to us developers, this mechanism is completely hidden. So on the surface, it does look as if a variable is actually holding the object itself, when in fact it's only storing the reference to the object behind the scenes. And that's actually a huge difference, as we're about to see. Because as we move on to the next line, here we create a copy of the location object called new location. And so here is where it gets really interesting. So if a variable like location simply contains a reference to the object, then as we copy the variable, what we're actually copying is only the reference to the object, but not the object itself. Or in other words, when we set new location to the same value as location, then we're simply copying the reference, because it's the reference that is stored in the variables in the stack. So in this case, this means that new location and location are pointing to the exact same object in the heap. And this is very different from how primitives work, where each variable actually holds its own copy of the primitive value, because there are no references involved at all. And this idea of object references has huge implications. So check this out. In the next line of code, we're mutating the new location object by setting its city property to Lisbon. So this is what that looks like in the heap. So far, so good, right? Well, not so fast, because what happens if we try to check out the original location object? And I think you can already start to see the result here just by looking at the heap and the references. So as we log the original location to the console, we now get the mutated object here, where the city property is also set to Lisbon. And this actually makes sense, right? If both location and new location contain the exact same reference that points to the same object in the heap, then it makes perfect sense that changing the object through one of the variables will also get reflected in the other one. Again, because location and new location are, in fact, the same object. In our case here, it means that mutating new location will destroy the value of the city property in the original location object. And I hope that you're still able to follow me at this point, but if this is super confusing, then don't worry. We'll actually explore this exact concept in practice by writing some code in the next lecture. But now, just for the sake of completeness, the calc_h function is actually, behind the scenes, also just an object, which means that this function also gets stored in the heap. And so then the variable calc_h will simply hold a reference to this object as well. So basically exactly the same thing that we just discussed a moment ago. Now this function had actually already been hoisted, so it actually was already in the heap all this time. Otherwise, we couldn't have used this function right in line 2, but we're just putting it down here at the end for educational purposes. All right, now to make sure that you really understood this super important part, as I just mentioned, let's jump back to our code editor and play around with this idea of object references and also learn about shallow and deep object copies.